Okay, the second part of this, so this is example 3, page 2. So we've already calculated the forces in the members. Now let's have a look at the same structure under a unit load, and as we said before, we want to apply the unit load at the position at which we want to calculate the deflection. So we want to get the deflection at the end of that member, and so we stick a unit load there of 1. So we could have that as 1 bar, but let's just call it 1 from now on. So that distance there is 12 meters. And the height is 3 meters. So if I take moments about that point, I've got 12 meters times 1, 12 meters times 1 kilonewton, and that must be equal to a force acting there in that direction there, and that must be equal to a force RB multiplied by 3 meters. And then from there I'm going to get the reaction at the horizontal reaction at B, and that's going to be equal to 4 kilonewtons in the direction shown. So I can mark 4 kilonewtons there. And then in terms of the horizontal equilibrium at that side, that's going to be 4 kilonewtons to be equal and opposite with the 4 kilonewtons up at the top. Now this member here, which is member 5, again can't take any vertical force, it can only take a horizontal force, so the entire 1 kilonewton that we've applied to the structure, that's going to be acting up there. So again, let's mark everything up in terms of tension. So I'll put tension forces in every single member. Tension force there, tension force there, tension force there, and then a tension force there, and then finally a tension force there. So we know that this member here must be in compression, so we'll stick a negative sign there, so that's going to be negative 4 kilonewtons. Now in terms of this member here, that's member 2, so we know that F2 sine alpha is going to be equal to 1 in order to be in equilibrium with the vertical force, and therefore we get F2 is equal to 1 over sine alpha, and that turns out to be 5 over 3. So we know that the force in this member here is in tension, and that's 1.67 kilonewtons. Let's just stick a kilonewtons there. So for this member here, we know that this member is going to be in compression because the vertical component of the 167 must equate, so that's going to be minus 1.67. For this member here, for the same reason, you look at that joint there. The only vertical component is this 1.67 in compression, and therefore this member here must be a 1.67 in tension. Now regarding member 6, which is the horizontal member, the horizontal member must be in equilibrium with the horizontal force of the 1.67 in member 2, and therefore it's going to be 1.67 times cosine alpha, and that's going to turn out to be negative 1.33 kilonewtons to be in equilibrium with the 1.67 in the horizontal direction. And then the last member, for which we've not considered, is member 1, so let's just do horizontal equilibrium at the top. We've got 4 kilonewtons minus 1.67 cosine alpha, which is 4 over 5, and that works out to be 2.67 kilonewtons in tension. So from there we have the we know the force in each member under both the unit load as well as under the set of real forces. So let's now come up with a table. So I'll say member, and then list the members 1, 2, 3, 4, 5 and 6. Now we want to know the length of each member. So the length of member 1, as we've said before, is going to be 8 meters. The length of member 2, as we've said before, is going to be 5 meters. That's the hypotenuse of 3 and 4, so the square root of 3 squared plus 4 squared. The length of member 3 is also going to be 5 meters. The length of member 4 is also going to be 5 meters. The length of member 5 we can read off as being 4 meters, and the length of member 6 is going to be 8 meters. Now let's work out EA, kilonewtons times 10 to the 5. So we're told that E is going to be equal to 200 times 10 to the 6 kilopascal, and that needs to be multiplied by A, which is going to be 0.0008 meters squared. So, knowing that 1 Pascal is equal to 1 Newton per meter squared, and that 1 kilopascal is equal to 1000 newtons per meter squared, or 1 kilonewton per meter squared. So we've got E equals 200 times 10 to the 3 kilonewtons per meter squared multiplied by 0.0008 meters squared, and that would work out to be 1.6 times 10 to the 5 kilonewtons. So the EA for all the values is 1.6 times 10 to the, well, I've put 10 to the 5 out there, so it's going to be equal to 1.6. 1.6 times 10 to the 5 kilonewtons, so for all of those values up there. Now let's put the n's and the n bars, and remember that the n bar in this case here is going to be equal to the 1 kilonewton which we've applied downwards, so that's going to be all, that's going to be to that value. So let's put in the values. Member 1, I'm going to put 2.67. Member 2, so that's member 1. Member 2, I'm going to be putting 1.67. Member 3, which is going to be that member there, that member 3 is also 1.67. Member 4, which is this member here, that's in compression, but taking our sign convention as drawing tension as positive, that we have to put the negative sign of 1.67. Member 5, which is this member here, that's going to be 4 kilonewtons in compression, so put 4.00. And then the last member, which is member 6, that's going to be equal to, that's in the member 6, that's going to be equal to the negative, so 1.33, so that's going to be in compression by 1.33. Now, going back to the previous page, where we calculated the values of n, we know that the value of, let's just tabulate this, so we know that the value of n in member 1 is 240. We know that the value of n in member 2 is 150, 300, minus 150, minus 480, minus 120. So the next step now is to multiply n by n bar, or n bar by n, multiply that by L, and divide that by EA. So we can again put that in units of meters and take out that as 10 to the 5, as we have 10 to the 5 down there. So multiplying 240 by 2.67, so multiplying our 240, which is our n for member 1, by n bar of member 1, which is 2.67, multiplying that by the length of the member and dividing by EA of 1.6. That gives a value of 3204. So for member 2, 150 times 1.67 times 5 divided by 1.6 gives a value of 783. For the next member, 167 multiplied by 300 multiplied by 5 and divided by 1.6, that gives a value of 1566. Now for the next member, both members are in compression, i.e. n is negative and n bar is negative. So since they're both acting in the same direction, that's going to be positive work. So again, 150 times 1.67 multiplied by 5 divided by 1.6, that gives you a value of 783 again. Next member, both are in compression as well. So obviously that should have been a negative sign for the compression. So 480 times 4 times the length divided by EA, that's going to give you a total of 4800. And then the last member, again two negatives, so you've got positive work done. Multiply 120 by 1.33, multiply that by 8 and divide that by 1.6, and you get a value of 7798. So if you added the whole lot together, you would get 11931, which would be the grand total. Now, just to reassess these values, that value is really 3204 times 10 to the minus 5, because if you multiply the 8 by the 240 by the 296 and you divide that by 1.6 times 10 to the 5, you'll get 0.032. So then if you move that by 5 decimal places, 1, 2, 3, 4, 5, so put more two zeros, then you will get that equal to 3204, to be a bit more accurate, times 10 to the minus 5. So just have a note here that you really do understand why that's 10 to the 5. That's just the format of the tables. But if you don't understand that, you can just forget about the 10 to the 5 and just work it out in the real units together. So therefore, the total vertical deflection, delta V total, is going to be equal to 11931 times 10 to the negative 5 meters. And then that is approximately, converting that into millimeters, dividing by 1,000, or timesing by 1,000, timesing that by 1,000 to turn it into millimeters, so away from the meters. So if we put the millimeters there, that turns out to be about 119 millimeters. So that's the theorem of virtual work to calculate the real deflection of the structure at the tip. And remember, at the tip is where you stick on your virtual force of 1 kilonewton, i.e. wherever you want the value of deflection to be calculated, that's where you stick on your unit load.